Math 2414, Taylor and Maclaurin series, video 4, Taylor Polynomials, Remainders, Taylor's Theorem. This video is going to get a lot more theoretical, as if the previous ones weren't. But I think it's important to understand what's going on in the big picture here. What we've done so far is we have used the formula for a Taylor series, and specifically a Maclaurin series, which is a Taylor series centered at x equals 0, to come up with a power series for e to the x. That series was e to the x is equal to the sum of k equals 0 to infinity of x to the k over k factorial. And if you're wondering why did I switch from k to n, or from n to k, for two reasons. Number one, to point out that the actual variable for the index is irrelevant. And number two, I got another use for n here in just a moment. But the actual polynomial was 1 plus x squared over 2 factorial plus x3 over 3 factorial, and we can carry that as far as we want. And when we did the ratio test in the previous video, we showed that the series converged for all x. But what we didn't show was that the series actually converges to e to the x. In other words, we showed this converged, but does it really converge to this? Where's the evidence? Am I just doing smoke and mirrors and trying to pull the wool over your eyes? Well, if you trust me, it does converge to e to the x, but math isn't built on trust. Math is built on irrefutable facts and logic. So we're going to go down the path of verifying that this series does indeed converge to this function, although we won't always do that in the future. I just want to show you how that works. In order to kind of address what I'm talking about, I need to first introduce something called a Taylor polynomial. Now, Taylor polynomial is actually a pretty easy concept. A Taylor polynomial, or rather I should say the nth Taylor polynomial for f of x. Excuse me, I just lost the, there we go. And remember, when you're doing a Taylor polynomial, you're talking about a general center, not x equals 0. So we'll just clarify that we are centered at x equals a. Is the first n plus 1 terms of the Taylor series for the polynomial. And you may be wondering, why is it the first n plus 1 terms? Well, I'll show you here in just a second. When you write a Taylor polynomial, you usually write it with a capital T subscripted with a number. For example, if I wanted the 0th Taylor polynomial for e to the x, then we would take 0 plus 1, one term. So it's just 1. It's this guy right here. But if we wanted the first Taylor polynomial, we would have to go to the 1 plus 1 or 2 terms. So we would go all the way out here. And our first Taylor polynomial for e to the x centered at 0. In this case, it could also be called a Maclaurin polynomial since our Taylor series was centered at 0. But our first Taylor polynomial is 1 plus x. What's our second one? Well, we would go out to 2 plus 1 terms, which means 3 terms. So it would be 1 plus x squared over 2 factorial. So why do we go out to n plus 1 terms? Well, that's easy. Because the degree of the polynomial matches the degree of the polynomial. So the second Taylor polynomial goes out to x squared. The first Taylor polynomial goes out to x to the first. The 0th Taylor polynomial goes out to x to the 0, so it's constant. So what's third Taylor polynomial? What's the series up until x to the third? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So for each Taylor series, there's an infinite number of Taylor polynomials. Now, why are we looking at Taylor polynomials? Well, namely because they are partial sums for the Taylor series, and a convergence of a series is defined by looking at the sequence of partial sums and seeing if that converges. So it's in perfect alignment with that. But I want to go to Desmos for a second to kind of give you a visual of the question we're trying to address. So let's share that. Desmos, where are you? There you are. Okay, so I've got a few things in here, and I'll explain what they are in just a minute. Here's the graph of e to the x. It's one you should know. Has an asymptote on the left, goes to infinity on the right, crosses at the y-axis at 0, no x-intercepts. And I've also set up a Taylor polynomial to take the sum of the Taylor series up to an upper limit of my choosing. Now, right now, that upper limit is set at 0. So that means we're looking at the 0th Taylor polynomial. But remember that that was just t0 of x is equal to 1, so it's a constant function. If we raise it to the first Taylor polynomial, which was 1 plus x, you'll notice that this line is the graph of 1 plus x. Has a slope of 1 and a y-intercept of 1. So it's correct 1. If we went to the second Taylor polynomial, we get that parabola. And notice that this parabola, when you get in kind of close, is pretty close to the red graph of e to the x. It's not perfectly lined up. In fact, you could zoom in and see that there's actually a gap between them. But the only place it's guaranteed to agree is at the center. So I could zoom in as much as I want here, and the red and the blue will always coincide there. However, I should be able to zoom in enough so that we do see some gaps between, give me 1 second. Well, okay, so that we should see some gaps between the red and the blue. It's not letting me zoom in anymore, which is really weird because earlier I was zooming in to 100 decimal place accuracy. But anyway, so if we stop at the second Taylor polynomial, we get a second degree polynomial whose graph is a parabola, and it's pretty close to the graph of e to the x, but we were supposed to have convergence on all real numbers. Right now, we barely get it in the middle. So let's see what happens if we tell Desmos to raise the degree of the Taylor polynomial. Right now it's a 2. We're going to take it all the way up to 20. I want you to watch what happens to the blue graph. Let me zoom out a little bit. I want you to watch what happens to the blue graph relative to the red graph. As we raise the degree of the polynomial, notice on the right side, we've already got pretty close graphs up there. We could zoom in and we could see that there's actually a gap between there, but it's pretty close. And if we, on the left side, however, we got this sudden drop off and it's nowhere near that. So I want you to watch what happens to the blue graph, especially over here where it's not seeming to line up much. As I tell Desmos to raise this, it's currently at the 5th degree Taylor polynomial. We're going to take it all the way to the 20. You'll notice that it flips up and down. That has to do with in behavior of polynomial functions, but it's almost like it's wrapping itself around the red graph over here. Right now we're at 14, 15. We'll take it a little bit further to 20. We'll stop it when it gets there, and there we are. We zoom out, you'll see that the blue graph is very tight over here on the right, but there's a point, it looks like it's a little bit here past -7, where the blue graph does what polynomials do on the end and go to infinity or negative infinity, and it doesn't flatten out. However, if we were to raise the degree of the polynomial even higher, we would get closer and closer to the red graph on the left end. All right, so yeah, our Taylor polynomials are approximating e to the x when you stay close to the center, but our theory is that if we did this forever, the blue graph would eventually overlap the red graph as far out as we wanted it to. But how do we show that theoretically? Well, in order to show that theoretically, we need to, give me 1 second to share Zoom. There we go. In order to show that theoretically, we need to talk about the difference between the function that we're approximating, e to the x, and the polynomial approximation of it, the Taylor polynomial. So we're going to define a new function called the remainder, and the remainder is exactly what it sounds like. It's what's left over. If you wanted to define it straightforward, we would say that the remainder, let me type this, hold on. There we go. Widen that text box. The remainder for the nth Taylor polynomial for, 1 second, folks. I'm sorry, I haven't even defined actually what I meant by a Taylor polynomial in general. We've just done the specific one for e to the x. So let's talk a little bit more generally here. So let's start with the nth Taylor polynomial. The nth Taylor polynomial for f of x centered at x equals a, because remember, when you have a Taylor polynomial or a Taylor series, the center can be wherever, is defined as, and I'll draw this, the nth Taylor polynomial is, it looks like the Taylor series. We'll start at k equals 0 of the kth derivative evaluated at a over k factorial times x minus a to the k. But the nth Taylor polynomial stops at n, so that the degree ends with n. So that's what I mean by the nth Taylor polynomial. Take the polynomial out to the nth power, and the remainder for the nth Taylor polynomial, and again, we're still centered at x equals a, is defined as basically it's defined as the rest of it. We're going to draw this. The remainder, so capital R, n for the nth Taylor polynomial, not Tyler polynomial. That's not even how you spell Tyler. I guess you could if it was a name. But the remainder for the nth Taylor polynomial is just the function that we're approximating minus this guy. So the difference between the true function and the nth degree polynomial. You could also look at this as saying that our function is equal to the nth Taylor polynomial plus its remainder. But its definition is, what are we approximating minus what are we approximating it with? Let's highlight that right there. Let's highlight this too. It's our definition. So you can think of it as the infinite tail, if you will, except it's not quite that. All right, so I want to show you real quick. Actually, before I go back to Desmos, I want to clarify what it means for a Taylor series to converge to the function that it's allegedly representing. So let's go to the next page and write that. And this is actually Taylor's theorem. Actually, hold that train of thought just for a second. Taylor's theorem. Yes, okay. Did I say Taylor's theorem or Taylor's formula on this first page? I said Taylor's theorem. All right, so yeah, okay, well, we'll call this Taylor's theorem because it is. I just want to make sure that I use the same name that the book is using, because I would hate to say one thing and then another. Actually, they don't call it Taylor's theorem, but I'm going to. Why? Because, well, it's my class. I can call it whatever I want, but we'll call it Taylor's theorem. All right, so Taylor's theorem goes something like this. The Taylor series for f of x will converge to f of x, so the series will converge to the actual function on some interval of the form a minus r, a plus r. Remember, we're centered at a, and we have some radius of convergence. If and only if, and here comes the theorem's conclusion. If and only if the limit as n approaches infinity of the remainder is 0. So let it all sink in. We defined a Taylor polynomial by saying take it out to a certain power. So it's like a Taylor series that stops. We define the remainder as the difference between the function that we're approximating and the nth Taylor polynomial. And we're saying that the Taylor series will converge. In other words, the infinite series, which in this example is this guy, we're saying that the series will converge to the function. That's what we're saying here. The series will converge to the function on the appropriate interval if and only if this limit is 0, which makes perfect sense because if you think about how Rn is defined, it's literally defined as f of x minus Tn of x. And so we're saying if and only if that. But the function is independent of n, so we can just not worry about the limit on that guy, and we can just put the limit on the Tn. So f of x minus the limit as n approaches infinity of the nth Taylor polynomial, that limit is equal to 0. But if we add the limit to the other side, it becomes positive, and we get something like this, which makes perfect sense because we're talking about the sequence of partial sums. Remember, the Tn is just a partial sum for our infinite series. And what it means for an infinite series to converge is for its sequence of partial sums to converge. So we want it to converge to f. So it really makes sense that the remainder has to approach 0. All right, so let's get rid of everything down there. Let's go back to Desmos for a second because I want to show you how this looks visually. Desmos, where'd you go? Here we are. All right, so let's take this all the way back down to the 0th Taylor polynomial, but this time I'm going to turn off both functions and I'm going to turn on this one down here. This equation down here is asking what is the original function minus the Taylor polynomial. Now, all we're saying is if our series converges to our function, then this difference should approach 0. So let's see what happens to this graph as we let the Taylor polynomial get higher and higher and higher. Right now it's the 0th Taylor polynomial. Now it's 1, 2, 3. Let's stop for a second. Notice that this is pretty flat here. It's almost equal to 0, which means as we're near our center, this difference is approximately 0, which means the function is approximately equal to the Taylor polynomial. As we raise the degree, and let's just go ahead and move it all the way up. Notice that it's a lot flatter now, meaning that the difference is closer to 0. In theory, if we did this forever, it would get even flatter. I'm going to manually put a 100 for the upper limit, give it a second to calculate, because I know it's going to take some time to do it. There it is. And look at that. Flat line. We killed it. Well, sort of. If we zoom out, it's going to take a minute to recalculate. At some point, this 100th degree polynomial will stop approximating e to the x so nicely, it's still thinking about it. It takes a long time for this computer to do 100th degree Whoa, I think I broke it. But regardless, we can tell that something funky happens when we get too far away. So for a 100th degree Taylor polynomial, we get a pretty good approximation, looks like between -30 and 30. But as we go further, the approximation gets worse and worse. But that's okay, because what I wanted to show you, I really wonder why I did that thing at the end. What I wanted to show you is that the difference is approaching 0, as you can tell by this purple line approaching, this purple graph approaching the x-axis as we let the Taylor polynomial's degree get higher and higher. So that's all the theory is saying. All right, let's go back to, come on. Let's go back to here, please. Thank you. All right. So I want to show you one more thing before we wrap up this video. And this is called Taylor's formula. That's why I kept going back and forth. I was like, something's called Taylor's something. And in the book, it was called Taylor's formula. In fact, I'll go ahead and share it with you real quick. I'll write it down, but I'll just show you where it is in the book. Let's go back here. Let's go to the book. Here it is. All right, there's Taylor's theorem. Here's Taylor's formula. Basically gives you an expression for the remainder. But the expression involves a value z that we don't know. Let me go back to the screen and I'll write it down and I'll explain what all the pieces mean. All right. Suppose f of x has a Taylor series centered at x equals a. And I can't type the subscript, so I'll say Rnx be the remainder for the nth Taylor polynomial. So in other words, it's equal to f of x minus the nth Taylor polynomial. And this is centered at x equals a, so let's assume that we have something for the radius of convergence. Let's assume convergence of the Taylor series occurs on a minus r, a plus r. So we got a representation for the Taylor series. All right. Then for every x in this interval, there exists some z, so here comes a new number, between a and x, such that, and here comes Taylor's theorem, or Taylor's formula, excuse me, the remainder evaluated at x is equal to the next derivative evaluated at z over n plus 1 factorial. Let's make this line a little bit shorter. Times x minus a to the n plus 1. Let me make sure I've got all that written correctly. Go back to the, here. Yes. All right. So what the heck does all this mean in this really long video? This means that if you have your number line, so let's draw a number line, and you're centered at a, and let's say over here is a minus r and a plus r. All this is saying is that if you pick any number x in there, then somewhere there is a z between a and x, so that our remainder is equal to this. If you really remember all of Calculus 1, you might start thinking, I've seen something like this before, and it was the mean value theorem about the existence of a value that makes something true. But that's all this is saying, is that we can find a number between the center and whatever x we put in that will give us the value of the remainder when we do this to it. Now, it is worth mentioning that the z depends upon two things, the x and the n, but we're not going to get that nitpicky about it. So why is this useful? Because if you want to show convergence of a Taylor series to the function it's approximating, technically you have to show that this limit is equal to 0. So if we can set up some expression and possibly show that the limit is 0, that's sufficient evidence that the series converges. I'm going to do an example. It was going to be part of this video, but this video has already gone longer than I wanted to, so we'll just have one extra video.